But the fundamental idea is actually quite simple. That when we're dealing with the genetic disorder, if you kind of visualize it this way, right? So there are like hundreds of different proteins and so on, and to a certain extent, you want to maybe associate it with their, like, you're building a house, and you get the factory, the kind of brick factory that delivers certain, you know, set of materials for you, so produces certain bricks. And the problem with the genetic disorder is that certain bricks, they just don't get produced. I mean, like whether it's consistency, whether it's the shape, whether it's whatever. And when one tries to sort of fit this missing bricks into their entire kind of composition of the house, so then you experience the challenges and things kind of don't go very well. So, but the general logic is always the same. That what we want is that when we look at it, we always look at it from two perspectives and saying, like what is the most general, take on the bodily tissues. And in fact, it's actually quite simple. So if we don't move even too far into the fascia thing, you can look it up anywhere, and there are just four basic tissues, right? So, and those four basic tissues are the connective tissue with all its potential sort of subsets, and then you've got the four other types of cells. So the epithelial ones, which are mainly the parenchyma of the internal organs. Then you've got the muscular cells, and you've got the neuron. So, and the key point is that this kind of two clusters, we want to divide them along these lines, right? So that connective tissue is, if we continue our example of the house, so that would be the the mortar, the cement, whatever the connection, which builds it, right? And then the cells, which are embedded into this uh, mortar, are the bricks. And if you look, there are two sort of basic types of constructions, right? So on the one hand, you can have this kind of regular houses made out of well shaped and well formed bricks, and then the mortar that just connects them is the one which pretty much just connects and doesn't really have much of the trouble, so the architecture builds quite naturally. And if you look at anything sort of semi-medieval or rustic countryside thing, so what you see there is that you can have all sorts of odd-shaped stones, which you just kind of collect locally. And if you just put them together sort of randomly and try to put just equally sort of thin and regular layers of this mortar, then it's not going to work. But on the other hand, what you see is that if there is a total architectural sort of plan, you can make things out of the most irregular building elements. You can make the working, functioning, stable structures. So that's really the idea, right? So that what we are taking there is that we're looking at the connective tissue in general and saying, well, how we can stimulate, how we can get the most out of this connective tissue, because this is the renewable thing. This is the one which is the most dynamic, which has the turnaround and so on. And this is really where your adaptation happens. And with ABR, this is what we really want, right? So we want to stimulate as much as possible the development, the kind of gradients, and the structural organization within this connective tissue. So that's our bigger take on dealing with those irregular bricks. So which are in essence, that's what the genetic disorders are, right? So you see, and genetic disorders, they come in all sorts of forms, right? So you see, it could be this type of bricks, or this type of bricks, or this type of bricks, and depending on what kind of brick uh, the brick factory produces with like some say mistakes, then you would have sort of different diagnostic labels, different sort of typical predictions and so on. But if you look at it from the connective tissue perspective, so your goal is always the same. So you want to contribute as much as possible throughout the connective tissue development and quality, and you also want to create the system which would be, you don't know the shape, but what you know is that what you want is the most effective distribution, right? So you see, in that sense, the more distributed, right? So you see, that's the key word. So we see, we want to create the most distributed. Well, my writing here is not doing very well. Most distributed. So distribution of loads is good. Concentration is bad, right? So you see, we don't want concentrations, local, uh, specific, excessive, you know, irregular, and so on. And we want really to maximize the distribution. So that's really the key idea which underpins everything.